Hi, I'm Joon from my design lab in KAIST, and we are happy to present our work, Body Follows Eye, Unobtrusive Posture Manipulation through a Dynamic Contents Position in Virtual Reality. In this study, we explored how to move a virtual object under user's perception threshold and unobtrusively manipulate user's posture in VR. We expect that virtual objects will be a part of the future workspace. Compared to the physical displays and furniture, virtual objects can be dynamically positioned around users and manipulated in real time during users' activities. Considering such property, many studies in HCI have adapted virtual contents to users. For instance, Harrison and they developed a system that magnifies the on-screen contents when users lean toward the display. And Maraki et al. Investigated making changes unnoticeable in users' FOV and demonstrated providing a solution in a puzzle game without users noticing. However, we lack knowledge on how the dynamic position of virtual objects influences users' posture. If we can estimate user responses, we believe that a system can improve users' health, comfort, or performance during their activities without needing their attention or effort. Therefore, in this study, we took the opposite approach and tried to move users' body by moving a virtual object. Our unobtrusive user manipulation is based on two key phenomena. The first phenomenon is the eyes lead the body that people compensate unsatisfied vision by changing their posture, such as leaning toward the music to see it better. Based on the phenomenon, we expect that users will follow a moving target not only with their gaze, but also with their body movements. The second phenomenon is the change blindness, that people fail to detect changes in their visual scene when the changes occur very slow during eye socket or blink. This phenomenon has been extensively explored in redirected walking, which is unnoticeably bending users' walking path in a physical space by moving a virtual environment at slow speed or during an eye blink. Based on the phenomena, last year we built a robotic monitor stand that slowly moves under users' perception threshold and corrects users' posture. In this year, we compared users' body movement, performance, and self-reported responses from both obtrusive and unobtrusive motions of a virtual content window. To make the motions unobtrusive, we moved the virtual content window at constant slow speed. The video on the left shows very slow right translation as an example. In addition to the constant speed, we also moved the content window during an eye blink in a bigger step. The reason that we explored both technique is to have additional gain and increase the overall motion speed without affecting the unobtrusiveness of the motions. To investigate user responses and explore design implications, our study has three parts. First, we systematically analyzed and estimated users' motion perception threshold on two unobtrusive motions. Second, we conducted a formative study to compare user responses on three selected motions in three speed conditions. And lastly, we designed three concept applications to explore design guidelines for unobtrusive posture manipulations in real time. Due to the limited time, I'll briefly introduce how we estimated unobtrusive motions and focus more on the formative study and concept applications. In both perception threshold studies, we tested translations and rotations along three axes for both directions. In VR, we performed two alternative first choice procedure. The participants observed the moving content window for a certain duration and had to choose the motion direction that they think the content window has moved. Even if they did not know because the change was too small, they had to take a guess and choose one between two opposite directions. We prepared 5 speeds for each direction, and participants repeated each speed for 6 times. In this way, we can make a probability curve like this. For instance, this is the result of forward and backward translation. The right end represents the probability of participants' responses, saying that the content window moved away from me after observing the motion. The left end represents the probability of the opposite response. In psychophysics, the blue area, which is the middle between 50 to 100% and between 50 to 0%, is considered as perception threshold. So in this case, the unobtrusiveness speed for backward translation is 2.56 mm per second and 1.89 mm per second for forward translation. Considering that a snail can move up to 13 mm per second, you can see that this is quite slow speed. For all the results and details, please check our paper. Next, in the formative study, we explored how users respond to a moving virtual content window during a reading task. In a 3x3 full factorial experiment design, we compared the influence of no motion, obtrusive and unobtrusive motion on users' posture change, task performance, and self-reported responses. So, based on the result of the two perception threshold studies, we designed three unobtrusive motions as shown in this video. The content window moved at unobtrusive speed and during blink until it reached the final position and angle. In case of the obtrusive motions, it moved the same distance and angle as the unobtrusive motions within 5 seconds. We conducted the study with one participant at a time. We introduced our study only as measuring the reading performance in VR and told the participants that they can freely move or resit to read the text better. Each participant experienced all three motion conditions, and we closed the study with an exit interview and survey. Based on the third experiment, I'll share 4 main results. The first result is about the unobtrusiveness of the motions. All participants commented that they did not notice when the unobtrusive motion starts, but later they noticed the displacement due to the updated position of the virtual content window compared to the background, as well as the angled edge. The second result is the participants' different body movements following the obtrusive and unobtrusive motions. This is the timeline of one participant's body rotation during left translation. The blue lines represent the relative angle of the content window to the participant's head, and you can see the participant's body rotation facing the content window in both obtrusive and unobtrusive motions. The main difference was that the obtrusive motions interrupted relaxing posture and triggered abrupt posture change followed by posture adjustment. In contrast, unobtrusive motions triggered the sequence of continuous body movements that participants switched between relaxing and moving. As you can see in this video, she tends to maintain leaning toward the target and follow the moving content window by pushing the chair with her legs. This behavior was also observed for backward translation. Following the obtrusive motion, the participants lean toward the target, find a comfortable distance, then lean backward again. Following the unobtrusive motion, instead of continuously moving in an upright posture, the participants repeat the sequence of leaning forward and backward as the content window constantly moves away from her. In case of the upward rotation, the participants tilted their neck and torso backward at once from the obtrusive motion. And in case of unobtrusive motion, they tilted their neck a little by little to maintain the comfortable viewing angle to the content window. The third result is the influence of motion on users' reading performance. We counted how many words the participants read to check their performance. The results showed that there was no significant difference between all three conditions. This is opposite to our initial hypothesis that obtrusive motions would degrade users' performance. We have an assumption on this opposite result and are presented in the next slide. The last result is about self-reported motion preferences. The participants considered their effort for posture change as well as reading. 7 participants preferred unobtrusive motions as they could focus on the reading. On the other hand, 5 participants preferred the obtrusive motion as they did not like changing posture multiple times from the unobtrusive motions. This is the reason that we think the obtrusive motion did not degrade the participants' reading performance in this study. We believe if the study duration was longer and the participants experienced multiple obtrusive motions, their reading performance and preferences on obtrusive motions would have been different. Based on the results, we designed 3 concept applications that prevent physical inactivity. The first application makes a user roll over from prone to supine posture. The second application triggers standing up from sitting. And the last application vertically oscillates around users to induce vision-based active sitting. We conducted an informal study with these applications and explored design considerations for unobtrusive posture manipulation. I will share 4 initial themes. The first theme is the moment of realizing the motion. Eventually, the participants realized that the content window was moving, which broke their focus on the content and harmed the unobtrusiveness of posture change. However, this break was also considered to be beneficial as it triggered voluntary and natural body movements. In current approach, it is inevitable that users notice the changes. Therefore, how users respond after noticing the change needs to be designed, such as assisting users to regain focus on the content or introducing bigger posture change. The second theme is the quality of posture change. Especially in the rollover application, the participants reported long uncomfortable postures between comfortable postures, such as lateral or hyperextension on their neck. With a classification of comfortable postures, future system would see such posture as transition and minimize the time spent in the posture with swift motions. The third theme is users' feedback to the manipulation. During the interview, all participants expressed the need to adjust the motions of the virtual content window, such as refusing to change posture or expressing to change posture in the other direction or at faster speed. As the system manipulates users' posture during their activity, a seamless interaction to adjust motions needs to be explored. For example, changing the motion direction or speed with swift head rotations. The last theme is the discomfort in the interaction. In case of dramatic posture change, such as sitting to standing up, the system had to overshoot the position and orientation of the virtual content window, which made the view uncomfortable even after changing the posture. We expect that users already lose their focus on the contents during dramatic posture changes. Therefore, the system should adjust the virtual content window in swift motions as users change their posture. As a conclusion, I'll present 3 discussion points. In ergonomics, active sitting has been proposed to continuously move users' lower body to prevent physical inactivity during a sedentary work. We also observed such continuous body movements, which needs to be distinguished from posture change that occurs abruptly as an event. By controlling how far the virtual object moves, we would be able to design whether we'll trigger only continuous body movements or lead to trigger posture change that would suggest users to take a break or stretch. Second point is the variations of obtrusive motions. The formative study and concept applications showed the need of faster manipulations for comfortable posture changes. Therefore, further investigations on the quality of motions would be required to understand how to make obtrusive but not intrusive motions. It would require to estimate at which speed users start to lose their performance and explorations on the motion profile, such as acceleration when the motion starts. The last one is the interface that controls users. Whereas we investigated posture manipulation with the moving virtual content window, we believe that there are many unexplored stimuli in dynamic workspaces that would influence users and can be investigated to support or correct users during their activities. For instance, furniture can be actuated to directly push users' body, or the movement in peripheral vision can be designed to stimulate frequent body movements. By understanding how users respond to such changes around them, we would be able to design workspaces that continuously support users without needing their attention or effort. This is the end of my presentation, and here are the takeaway messages. For any questions, please contact us through the email address below, and thank you for listening.